Today we are talking about probability. And to talk about probability, we got to start by talking about sets. A set is a collection of objects. Most often in probability, those objects are numbers or are related to numbers, but they don't have to be at all. So a set can be finite, or it can be infinite, or it can be empty. For example, the set of states beginning with the letter O. So we would call that set O, and it would include Ohio, Oklahoma, and Oregon. And this is a finite set because that's the whole set. It doesn't just keep on going forever. That's all the states that begin with the letter O. If we had instead something like the set of prime numbers, remember, prime numbers are numbers that can only be divided by 1 and by themselves. So we might call that set P, and it would include 2, 3, 5, 7, 11, 13, 17, 19, and it keeps going. There's no end to the prime numbers. They go on forever. So we would just say ... to indicate that this set continues on indefinitely. And this would be an infinite set. And if we had something like the set of multiples of 4, that are odd, there are none, right? Multiples of 4 are 4, 8, 12, 16, 20, 24. All of these are even numbers, and they always will be because 4 is an even number. So this would be an empty set or a null set, and we could show it that way, or you could write brackets with nothing in between them. Either one of these would be a way of showing an empty set. Now, a universal set contains all possible elements for a certain problem or situation. And it is denoted as U. The complement of a set is the set of all elements from the universal set that are not in the original set. And we write it as, like say we had set A, the complement of A would be like this, or like that. So if we had a universal set that was 1, 4, 7, 10, 12, 15, 17, 20. So that's the universal set for a given situation. And set A equaled 4, 10, and 17. The complement of A would be all the numbers from this set that are not in this one. So 1, 7, 12, 15, and 20. The intersection of two sets is the set of all elements in both. And the final piece of vocabulary about sets, the union of two sets is the set of all elements that are in either. So to be clear, if you have two sets of numbers, the intersection is all the numbers that appear in both sets. So if there's a 1 in this set and a 1 in this set, the intersection would be 1. So they both have to have the number for it to be part of both sets. The union is when you combine the two sets and it's just everything all thrown into one pot. So you put the two sets together and it's their combined elements. Okay, we have some more vocabulary to cover really quick before we get to the actual page. So I'm going to move to the back side of my paper. So an experiment in probability is an action with varying results. So you're doing something and you're not positive what the outcome is going to be. There are different possibilities. So like, for example, rolling a die. The outcome of the experiment is a possible result. For example, if you roll the die, you could roll a 2. That's a possible outcome. The sample space is the set of all possible outcomes. So for rolling a die, that would be 1, 2, 3, 4, 5, or 6. Those are the possible numbers you could roll with one die. So this is very straightforward, but sometimes we're doing multiple actions, and so it can be hard to figure out what are all the possible outcomes, what is the possible sample space. So for that, we often use a tree diagram. So let's say that we were rolling a die and then tossing a coin. I'm going to draw this out as a tree diagram. So first, there are 1, 2, 3, 4, 5, 6 possibilities for rolling a die. I could roll a 1, a 2, a 3, a 4, a 5, or a 6. And then after I roll the die, I could get 2 possible flips of my coin. I could get heads or I could get tails. So those are my possibilities. So my sample space I could roll a 1 and get heads. I could roll a 1 and get tails, 2 heads, 2 tails, etc. And write down each one of these possibilities. How many total outcomes? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Twelve possible outcomes. Now, maybe this still seems a little bit tedious to you, right? I have to draw out all these possibilities. I have to list all the possibilities. I have to count all the possibilities. This is where the final piece comes in, the fundamental counting principle. If one activity can occur in m ways, And another activity can occur in n ways, then both activities can occur in m times n ways. So there are 6 possibilities for rolling a die. There are 2 possibilities for flipping a coin. 6 times 2 is 12. So a couple examples. What if we were randomly choosing a month and picking a digit from 1 to 9? That would be 1 of 12 months and 1 of 9 digits. 12 possible outcomes here times 9 possible outcomes here means 108 possible combinations. What if we were choosing an outfit from 3 pants, 5 shirts, and 2 belts? 3 possible pants times 5 possible shirts times 2 possible belts means a total of 3 times 5 is 15 times 2 is 30, 30 possible outfit combinations. What if we roll a die 4 times? Each time you roll, there are 6 possible outcomes. 1, 2, 3, 4, 5, or 6. So 6 times 6 for our second roll, times 6 for our third roll, times 6 for our fourth roll. 6 times 6 times 6 times 6. 1,296 possible outcomes. Okay, now that we've established those basics, we're ready to talk about theoretical and experimental probability. So probability is a measure of the chance that a specific event will occur. When all the outcomes are equally likely, the theoretical probability of an event is the ratio of the number of favorable outcomes to the total number of outcomes. So number of outcomes that we want divided by the total number. Probabilities have values between 0 and 1 and can be expressed as a fraction, decimal, or a percent. So let's say we spin this spinner 1 time. What is the probability in a fraction, decimal, percent of each of these outcomes? So what's the probability that we'll get a multiple of 3? What are the multiples of 3? 3, 6, 9, 12, 15. 1, 2, 3, 4, 5 possible outcomes. So those are the 5 of the outcomes that we want over the total possible number of outcomes, which is 16. So that's the fraction. And if we could simplify this fraction, we would do that, but we can't. So this is where it is. To convert this to a decimal, we just do 5 divided by 16. That's our decimal, 0.3125. And then to convert a decimal to a percent, we move the decimal 2 places over, so that would be 31.25%. So there's a 31.25% chance of spinning a multiple of 3. Okay? What is the chance of spinning an even number or a number greater than 5? So either of those 2 outcomes. Well, there are 11 of these numbers that are greater than 5, plus 2 more even numbers. So that's a total of 13 possibilities. So 13 out of the 16. 13 divided by 16 is 0.8125. So that's the decimal. And then if I move the decimal 2 spaces over, that means there's an 81.25% chance that I'm going to spin a number that's either even or greater than 5. Okay, let's answer a few of these as fractions in simplest form. A pencil box contains 5 red, 12 blue, 10 green, and 3 yellow markers. If a marker is chosen at random, what's the probability that it's not yellow? So how many markers are there total? 5 plus 12 is 17, plus 10 is 27, plus 3 is 30. So 30 total markers. And out of those 30, how many of them are not yellow? All but 3. So 27 of the markers are not yellow. We can simplify this fraction. You could put it in the calculator and hit the simplification button. So you would get 9/10. So there's a probability, 9 out of 10 probability that you're going to draw a marker out that's not yellow if you grab one at random. What is the probability of drawing an ace or a diamond from a standard deck of playing cards? Anytime you take a test that involves probability, there's a good chance they're going to ask you something about a standard deck of playing cards. Some people may or may not know what's involved with a standard deck of playing cards, so it's good to talk about these questions. There's a total of 52 cards in a deck. Each deck of cards has 4 suits: hearts, diamonds, clubs, and spades. If we do 52 divided by 4, that's 13. So there are 13 diamonds because they're split evenly. And one of those diamonds is an ace. Then there are 3 other aces on top of that. So 13 diamonds plus the ace of diamonds, counting the ace of diamonds. And then there's the ace of hearts, the ace of spades, and the ace of clubs. That makes a total of 16 additional, or 16 total cards to choose from. So if we randomly draw out of 52 cards, 16 of those are going to be either an ace or a diamond. And I can simplify this in the calculator. 16 over 52 is going to get me 4/13. So 4 out of 13 cards would be an ace or a diamond. Finn guessed on the last 3 true or false questions on his math quiz. What's the probability he got exactly 2 questions correct? So if he got 2 out of 3 correct, the possibilities are that he got the first 2 correct and the last one incorrect. Or he could have gotten the first one correct, the second one incorrect, and the last one correct. Or he could have gotten the first one incorrect and then the last 2 correct. So those are my possibilities. You could map this out with a tree diagram. So the first question, he's got an equal chance of getting it correct or incorrect because it's true or false. So it's either correct or incorrect. Then the second question, if he got it correct, he could have gotten this one either correct or incorrect. But the same thing happens here. If he got the first one incorrect, then the second question could be either correct or incorrect. And then for each of these possibilities, we move on to the third question, which could be either correct or incorrect. So how many paths are there to the end here? 1, 2, 3, 4, 5, 6, 7, 8. So 8 total possible outcomes. Out of those outcomes, 3 of them are 2 correct and 1 incorrect. So there's a 3 in 8 chance that he got 1 wrong out of the 3. Students in a homeroom were asked if they have a part-time job and if they have their driver's license. The results are shown in the Venn diagram to the left. If a student from the homeroom is chosen at random, find each probability. So first we need to know how many students are there in this class. There's 4, 8, 6, 7, that's 12, that's 13. Add them all together, we have 25 students in this class. 4 of them don't have a part-time job or a driver's license. 8 of them have a part-time job but no driver's license. 7 have a driver's license but no part-time job. And 6 have both a part-time job and a driver's license. So out of 25 students, how many have a part-time job? 8 and 6, 14. Out of 25 students, how many have no driver's license? Well, 13 have a driver's license, which means the other 12 don't. Out of the 25 students, how many have both a part-time job and a driver's license? 6. Out of the 25 students, how many have either a part-time job or a driver's license? All but 4, so 21. And out of the 25 students, how many have a driver's license but no part-time job? 7. Again, I remember from earlier that the complement of a set is all the things that are not in the set. So the complement of an event is the probability of the event not occurring. Since the sum of all probabilities in a sample space is 1, the probability of an event not occurring is 1 minus the probability of the event occurring. So for example, the probability that it will rain tomorrow is 11 out of 15. What's the probability that it will not rain? 1 minus 11/15. Remember, 1 of the fraction can be any fraction that's the same on the top and the bottom. So 15 over 15. 15 minus 11 is 4. So 4 out of 15 is a chance of that not occurring. A number from 1 to 30 is selected at random. What's the probability of not selecting a multiple of 4? How many multiples of 4 are there between 1 and 30? 4, 8, 12, 16, 20, 24, 28, 7. So the probability of this event is 7 out of 30. 1 minus 7/30ths. And again, we could think of this as 30 over 30. 30 minus 7 is 23. So the probability of not selecting a multiple of 4 is 23 out of 30. Now, finally, experimental probability. Experimental probability is what happens when you take the probability in theory, which is that the odds are perfect and everything comes out exactly like it should, and put it to the test in the real world. Like if I flip a coin 50 times, theoretically, there's a 50-50 chance it'll be heads or tails. So 25 times it should be heads, 25 times it should be tails. But of course, if you flip a coin 50 times in real life, that's not how it's going to come out. The way it comes out is going to be your experimental probability. So if we spin this spinner, every one of these color options has an equal size on the spinner. So there's a 1 in 5 chance that you're going to get any one of them. But you can see here that we got them all different amounts. If I spun it 50 times, theoretically, I should have gotten 10 of each color, but I didn't. So the theoretical probability that we would spin it again and get orange is there's a 1 in 5 chance. The theoretical probability we could spin it again and get red or green is a 2 out of 5 chance, because those are 2 different colors out of the 5 possible colors. The theoretical probability that it will spin it and not land on purple, there's 4 colors that are not purple, so it's a 4 out of 5 chance. Now, what's the experimental probability of spinning again and landing on orange? Well, based on our past experience of doing this, there's a 12 out of 50 chance of spinning the spinner and landing on orange, which we could simplify to 6 out of 25. So slightly more than 1 out of 5. What's the possible probability experimentally of spinning again and getting red or green? Well, we got red 5 times and green 10 times. So there's a 15 out of 50 chance that we would get red or green, which simplifies to a 3 out of 10 chance, which is lower than 2 out of 5. And what's the possibility of not landing on purple? Experimentally, they landed on purple 7 times, which means they landed on the other colors 43 times out of 50. So slightly higher than a 4 out of 5 chance. So that's experimental versus theoretical.